All right, we ran out of time today, so I wanted to just go through a last couple details about standing waves, so you have that advantage of knowing it. So I really kind of outlined what would happen or how we would create a standing wave. And a standing wave, while waves are going back and forth on, say, a string, the pattern that you actually see, so say I have a string connected between 2 points. When there's a standing wave, the string is vibrating constantly as the waves travel back and forth. But what happens is you sort of see the blur of the strings it's vibrating up and down, but then you kind of see an outline. So it might look something like this, or it might look something like this. So, there's different modes of how the wave is going to be traveling and what kind of standing wave is going to be set up. And basically, the things that are involved with creating this standing waves is, first of all, we have to understand the reflection, how the waves reflect when they hit a boundary, and then also how they interfere. How they interfere is how they behave when they are, getting to the same location at the same time. So let's look at both of those. I did kind of talk about it, but I want to make sure that I really give a good explanation. So the first thing we have to figure out is, okay, we have a wave traveling on a string. That's going to be our medium. And let's say that the string has two ends, obviously. That's how it happens. Now, as the wave goes down the length of the string, is it going to hit a boundary where the string is like clamped so it can't move? Or is the string going to be like maybe looped around a vertical bar so that it actually can go up and down once it hits that boundary? And which one it is going to be important because the wave, as it reflects, behaves differently. So first of all, if we have a wave that hits the boundary, but it's fixed at that end. So the wave is clamped the wave is clamped at this end. It's a fixed boundary. What happens is when the wave comes in, like so here's the peak, and it's kind of like pulling up on the boundary creates an equal and opposite force, pulls down on it. And so that's what happens why the pulse here, where the pulse is pointed up, because of this reactive force at the boundary, when it hits that boundary, it actually gets inverted. So a fixed boundary is going to create an inversion on reflection. Now, the opposite happens, or we could say nothing happens if the boundary's free. And this is where I was trying to describe, like you said, have a vertical pole and the string is like looped around it, but it's free to move up and down. And so as this pulse comes in, once it hits this boundary, what happens is this loop will just move up very easily as the pulse gets to that location, and then it reflects, and nothing happens to the pulse. It's just totally reflected with the normal orientation that it had coming in. So those are the two possibilities of how the wave is going to reflect. And so that's one thing to consider when we're setting up standing waves. But if you think about it, if I have a constant wave coming in, so you have one wave coming this way and one wave going that way, then we want to think about how do these add together. That becomes the second thing about. And that has to do with what we call interference. When two waves get to the same location in space at the same time, they're going to interfere with each other. And what we want to know, how do they interfere? Like, what happens when the two waves get to a location at the same time? And the principle of superposition is what governs how they're going to interfere. And basically, it's just that the total displacement is the sum of the displacements of the individual waves. You just add them together. So I showed this picture in class, and I think it's still worthwhile looking at. And so we have two wave pulses coming towards each other, and we're going to see how they interfere. And simply their displacement, so their y values here, add together wherever they overlap. And that's why, for instance, as they get closer together, this little piece isn't down at y equals 0, because you had a little bit of the tail of each of these pulses are overlapping, and so you add them together, and that's why this piece is just a little bit up. When you get to they're exactly alike, it's like when you had the two waves are at the same location at the same time, and so you just add those two pulses together, and that's why you get this higher pulse. And then you see they continue to move through each other. And to be honest, that's one of the really cool things about waves, is how they interfere with each other. And so when they're at the same location at the same time, they add together. But then they just kind of move on move on the way they were, and then it's like it never even happened. So isn't it interesting that how we start off with it looking like that when they're coming at each other, they move through each other, they add together, but then they just continue on and on their merry way in the same direction they were moving originally. And it's like nothing happened to them. They weren't changed by the interference. Like the waves itself persisted. They just add together for a moment and then they move on. This is another picture that I showed you from that was in class but was from the textbook. And I really like this because it's kind of getting down and really into the details of how the two waves interfere. So as I mentioned, so you have one wave. The red one was, we could say, was Y1. That's one wave. And the blue one is another wave. That's called Y2. And the black line represents the two waves added together. And here what they're trying to show you is, for instance, what they've done is they take this little block right here and they're blowing it up in this picture so you can get a better look at it. And they're trying to show you that when we add the two waves together, so they said at this particular location in space, the y amplitude of wave 1 was 8 meters. The y amplitude of wave 2 was 10 meters. But because they're at the same location at the same time, the total amplitude of the two waves when they interfere is just 10 plus 8. It's 18. And so the black line really represents the sum of the blue and the red at every location. And so while there might be at some instant in time, keep in mind that this is like a snapshot. This is some particular t value. I don't know what it is. We could call it whatever we want. But even though the blue wave and the red wave are located or in this picture, we don't actually see them. All that we would see would be the black wave, which would be the sum of the two. And then if they're moving in the same direction or if different directions, the black line would just be changing as the waves are moving. It would just be changing its height and what it looked like. A lot of times when we describe interference, we talk about whether it's sort of the two extremes, which we haven't really looked at right yet, is constructive interference and destructive interference. And this is something we're going to come back to at the end of the semester, so it's good to remember this. So in this picture here, we have, again, blue plus red is going to equal to the black wave. So we have one wave we're calling Y1, and we have another wave we're calling Y2. Y1 is the blue one, Y2 is the red one. And notice they look exactly alike. They're meeting their high points at the same location, they're meeting their low points, and they also are going to 0 at the same location. They're exactly in phase with each other, and so when these two add together, everything adds together in a constructive way. So this is called constructive interference. You end up, because you have two identical waves completely in phase with each other, when they add together, you get one wave that just has the amplitude, twice the amplitude of one of the individual ones. The opposite situation here is what we call destructive interference. Notice that the peak of the red corresponds to the trough of the blue and vice versa. And so what happens is, because these two waves are exactly out of phase with each other, when you add them together, you get nothing. So you could actually have sort of, say, a string that was completely flat that would actually have these two waves running through it, but because they're destructively interfering, you never get any sort of amplitude. This was the video that I showed, and so I'm gonna also post the links to the videos that I wanted to show you, or I think I got to show you all but one of them. And so I'm gonna post those also on Sakai. But this was a question where you had like sort of a thicker piece of string, and then it got thinner, and you had a pulse that was moving through it. And what we're doing is we're sort of treating this as a boundary. And to try to think about like, how is the wave pulse going to behave when it gets to that boundary? And so in a sense, we're asking ourselves, is this going to be fixed or free? And if you think about it, if you're going from a more massive string to a thinner string, the thinner string is really going to create less of a resistance to the wave pulse. So that's going to be like a free boundary. And so that means that the reflected wave that comes off of that boundary is going to be like that. Nothing's going to change about it. And it's also going to transmit as well. So that's the thing that's a little different from the boundaries we looked at before. You know, when the string was attached at one end, there was nowhere for the pulse to go. But in this case, you actually have more string, so the wave can continue. And so at this boundary, there's actually going to be transmission and reflection. But in both the cases, the pulses that are reflected and transmitted are both right side up. This was also an exercise I wanted you to do, and so I hope you try it yourself, because I wanted you to sort of think about, with a simple waveform, how the two waves would interfere with each other. And so we're told wave A, is moving with a speed of 2 meters per second to the right, and wave B is moving to the left with a speed of 1 meter per second. You know, I made up this example on the fly, and it really doesn't make sense that they would move differently, but we're just going to keep it like that. So I wanted to say, what would things look like at 1 second, 2 seconds, and 4 seconds? So in 1 second, A would go to the right. Like, how far would it move? It would move 2 meters. And so B would move to the left, because it's only moving 1 meter per second. It would go to the left 1 meter per second. And so I can use that to help me draw what the waveform would look like. So if A moved 2 meters, so it would go from here to here. So if this was 4 meters, now this would be the beginning of where wave A would be, because it moved 2 meters to the right. So now instead of going from 2 to 3, it goes from 4 to 5. And then B just moves to the left 1 meter. And so this is what like B looks like. And so the outline of the wave that we would actually see, which would be the sum of the two, would be this black line. Okay? I'm going to do one more, and then I want you to try to do the last possibility. So at t equals 2 seconds, A will have moved to the right. In 2 seconds, it'll go 4 meters, and B will move to the left 2 meters. And so A went 4 meters in the 2 seconds, so it would have moved from 2 to 6. So this is where A is. It stops at 7. B would have moved 2 meters to the left, and so its beginning is at 4, and it's 5. So this is where B is. B's going this way, A's going this way. And so the sum of the two, which I'm going to use outlined in black, it actually is going to look like this. Okay, and again, that's just a really simple example of I'm really using superposition by drawing each of the pulses individually and thinking about how they add together. And again, why don't you try to do it for 4 seconds. Now that we sort of have that background, we can think about the standing waves and how we make those. And so we want to use a periodic wave, periodic traveling wave, and we're going to send it down a string and we'll allow it to reflect back. So this is the wave that goes to the right, and this is the one that goes to the left. So this one would be the reflected wave, and this one would be the incident wave, the wave that starts it off. And, this is just the principle of superposition here, saying that the sum of what we see is just going to be the sum of each individual wave. This is wave 1, this is wave 1, and this is wave 2. But as I did in the video, you can really kind of simplify this by using trig identities to rewrite these expressions. And so there was a lot of algebra involved. It isn't something that I want to spend my time doing in class. And so we come up with this solution of what the standing wave looks like. Now this is really interesting because in a sense, this piece, to me, I think of as the amplitude of the envelope, because if you look at this picture here, the motion or the string is moving, but it sort of stays within this envelope right here. And this value kind of tells you like how far am I sort of deflected from y equals 0. And notice that this value does depend on where you look, because it depends on x. And then this is just telling you that there's also this dependence at a particular x on time, because at a particular x, it's going up and down and up and down and up and down. And so this is the expression that really, for us, describes what the standing wave looks like. Now, we can do more with that, but let's note here was the amplitude of the original wave. Another picture. So when we look at the standing waves, first of all, there are places where we have what we call antinodes. This is the antinode, and this is the node. And so this is where the total amplitude, of course, is equal to 0. And then here is where it's actually equal to 2 times A, where this was the amplitude of an original wave. If we just go back really quickly to the... Okay, so where are we going to find the nodes and the antinodes? And so let's just remind ourselves of what our expression was that we were working with. So it's this piece right here that's going to help us figure out where the nodes and the antinodes are, because this is going to tell you the x values where those occur. And so if I want to find a node what I'm going to say is that 2a sine of kx is equal to 0, which also can be written as sine of kx is equal to 0. For the antinodes, we're saying 2a sine kx is equal to 2a, or the sine of kx, and I can make that plus or minus, is equal to plus or minus 1. And so here we're trying to think of kx is the values where the sine is equal to the sine of the angle is equal to 0. So where is the sine 0? Well, it's at 0 at 0 and pi and 2 pi, etc., right? And from that, I can figure out where the x values are. So it's sort of like n pi over k, where n is equal to 0, 1, 2, etc. Here, sine of kx, it's kx is equal to pi over 2, 3 pi over 2, etc. And again, we can solve for x equals. And so they go into a lot of details in your book, like how you find those, and that's fine. But to me, there's also a simpler way to look at it by looking at the pictures and thinking about what's going on. So for instance, let's look at this picture. Now, when we create standing waves, there's certain patterns that are going to happen. For instance, if we have a wave where the string that the waves is traveling through is clamped at each end, then you always have nodes at either end. And so there's only certain patterns that are going to come out. And you sort of start with the simplest one, and then you move to the more complicated ones. So the first one here is, if we look at it, it just has one antinode in the middle. And then you want to think about, okay, the total length of the string here is 2 meters. How does the length of that string compare to the wavelength? And I go, well, here I only see a half a wavelength. So the length of the string is equal to a half a wavelength. And then this is also called the fundamental, because it's the simplest wave that can be set up here. And we'll go into a little bit more detail. I'll do it in the next slide, but when we're talking about this, we're talking about frequency, but I'll talk in the next slide about how we would find the frequency. In the second picture, we have the next level complication is the one we have two antinodes, yep. And the length of the string is equal to just one wavelength. This is called, so this is the fundamental or the first harmonic. This is the first overtone or the second harmonic. And then finally, the next one is with 3 antinodes, and that you can see that you see 1.5 wavelengths on this string. So we have here, and this is the second overtone or the third harmonic. Okay, and so let's just remember more information. And here they found the wavelengths. And I did say that these correspond to the frequencies, so let's just say from the tension and mu, we know the velocity of the wave. And so the velocity of the wave is not negotiable, but given the velocity and the wavelength, the frequency is going to be given by this velocity over the wavelength. So the fundamental frequency we can find once we know the velocity and the wavelength of the wave for the standing wave. So this is the fundamental. And then F2 would be V over lambda 2, and that would be the second harmonic, etc. So that's, in the last slide, maybe it was confusing about what we meant by frequency, but when you get here, then you actually can see that, how that's working. And finally, here's a question. And so in this problem, we're setting up standing waves. And so see if you can figure out what the harmonics are for this. And so I'm assuming that both ends are fixed. I'm going to say ends fixed at both ends. And so this is how we create the tension. So the tension is equal to mg. And so that's equal to, 2 times 9.8. And then we're told the mass per unit length. So we can figure out the velocity of this wave is 2 times 9.8, because the tension is caused by the weight that's hanging, and then 0.006, and I got 57.2 meters per second. Now, the length of the string is 2 meters. If I set up the first 3 modes, this is going to be the first one, where 2 meters, which is the length of the string, ends up to be half of the wavelength. The second one is going to be the wavelength is equal to 2 meters. And then the third one looks like this. And so that the length is 1.5 wavelengths. And so this would be 2. And so we can find the frequency 1 is going to be 57.2 divided by 4 meters. The frequency of the second harmonic is 57.2 divided by 2, etc. And what you're going to see also, once you do these numbers, is that the frequency of the harmonics is just n times the fundamental frequency. That's something kind of fun. So this is actually an example from the book, so I don't feel bad about not giving you all the answers, but see if you can work it out on your own. All right, so hopefully that's a little bit helpful to finish up the material from this chapter.